Welcome to the deep dive. We've got a really interesting task set for us today. One of you is getting ready for the CSIR Junior Secretariat exam and send us a whole batch of general science questions.
Right. Quite a collection.
So our mission really is to go a bit deeper than just the answers. We want to unpack the core science ideas tucked away inside these questions.
Exactly. Think of it like building up a solid foundation. Useful for the exam, sure, but also just for, well, understanding the world a bit better.
Yeah, definitely. We're looking at multiple choice questions here covering physics, chemistry, and biology, all with explanations.
Which is great, actually. It gives us a structured way to look at a whole lot of key scientific concepts and, importantly, how they link together.
And we know you, our listener, want to get this knowledge efficiently, but also, properly understand it.
So we're aiming for those aha moments where things just click. Exploring the why without getting bogged down in too much jargon.
Okay, sounds like a plan. Let's dive straight in. First theme, units and measurements. Kind of the language of science, isn't it?
Absolutely fundamental.
Yeah.
So question 1 kicks us off asking for the SI unit of electric current. That's the ampere.
Ampere, okay.
But what is electric current? It's essentially the rate at which electric charge flows. Like counting electrons moving past a point each second.
Right, like water flowing in a pipe, but with charge.
Exactly. And interestingly, the ampere itself was originally defined based on, well, the magnetic force between wires carrying current. Shows how interconnected these things are.
That's neat. And just to clarify, the other options there were volt.
Yeah.
That's the electrical push.
Potential difference, yeah. The driving force.
Which is resistance.
How much something resists the flow.
And watt, which is power. We'll probably get to that one later.
We will.
Okay, next up, question 14, SI unit of force. That's the Newton.
The Newton, right. It measures a push or a pull, basically something that can make an object speed up or slow down or change direction.
Force causes acceleration.
Precisely. And what's really useful is seeing how it connects to other units we just mentioned. Force acting over a distance does work, and work is energy, measured in joules.
Ah, joules was another option there.
It was, and the rate you use that energy, or do that work, is power measured in watts. See, force, energy, power, Newton, joule, watt, they're all linked.
Okay, that makes sense, like a family of concepts. Now, question 31 loops back to electrical resistance. The unit is the ohm.
The ohm, symbol omega. So if volts are the pressure pushing the amperes, the current.
Then ohms are like the friction in the wire.
That's a great analogy, yeah. It's the opposition to that current flow. And the relationship between them, volts, amps, ohms, that's Ohm's law. Super important for circuits.
Right, V equals IR.
You got it. Then question 99 gives us the watt again. The unit of power.
So not just how much energy, but how fast you're using it.
Exactly. It's the rate, joules per second. A 100-watt bulb uses 100 joules of energy every single second.
Gotcha. Okay, question 46 asks about the unit of electric charge itself, the coulomb. How's that different from the ampere?
Good question. The ampere measures the flow rate of charge. The coulomb is the actual amount of charge. Think of coulombs as the packets of charge, and amperes as how many packets flow past per second.
Ah, okay. So 1 ampere is 1 coulomb per second.
Precisely.
Next, question 64. The SI unit of frequency is hertz. We hear that a lot, like for sound or radio waves.
Hertz or hertz is just cycles per second. How many times something happens or repeats in 1 second. A 440 hertz sound wave means the air pressure is vibrating 140 times a second. Gives you the pitch.
Simple enough. Moving to magnetism, question 243 asks for the unit of magnetic field strength. The Tesla.
The Tesla, yeah. Named after Nikola Tesla. It measures how strong a magnetic field is, the region around a magnet where you feel the force.
Like around an MRI machine. Those are powerful magnets.
Extremely powerful. Measured in Teslas, it quantifies that force field generated by moving charges or magnets.
Okay. Question 199 covers luminous intensity, the candela. This one sounds a bit more specific.
It is a bit. Candela measures the brightness of a light source in a specific direction, weighted by how sensitive our eyes are to different colors of light.
So not just the total light, but how bright it looks to us in one direction.
Exactly. Think about spotlights versus floodlights. Same bulb, maybe, but different candela values in the beam.
Interesting. Okay, let's look at derived units. Question 206 is about the joule, the unit of energy. It breaks it down into base units. Kilograms, meters, seconds.
Yeah, kg and ounces. What's elegant about this is how it shows energy is fundamentally linked to mass, distance, and time. It wasn't just plucked out of thin air. It comes directly from the physics of how forces do work.
Right. connecting the fundamental building blocks.
Mm-hmm.
And we also saw some of those fundamental SI units mentioned directly. Question 216, the second for time.
The absolute bedrock. Now, based on atomic clocks, incredibly precise.
Question 256, the mole for the amount of substance. That involves Avogadro's number, right? That huge number. Yeah.
That's the one, yeah. About 6.02 times 10 to the 23rd. It's the bridge between counting atoms or molecules and measuring amounts we can actually handle in the lab, essential for chemistry.
And question 266 mentions the ampere again as a fundamental unit for electric current.
It is. So you have mass, length, time, current, temperature, amount of substance, and luminous intensity. Those are the 7 SI base units everything else is built from.
A complete system. Okay, let's switch tracks entirely. Biology and health. Question 2 asks about communicable versus non-communicable diseases.
Yeah, a really important distinction. Communicable diseases are the ones that can spread from person to person. Think infections caused by viruses, bacteria, fungi, parasites. Measles, TB, flu are examples here.
But infectious.
Right. Non-communicable ones, like diabetes in the example, aren't typically caught from someone else. They often involve genetics, lifestyle, environment. The key is transmissibility.
Got it. Question 4 takes us to photosynthesis, a classic school topic. What's the main thing to remember?
The absolute core is that plants use sunlight, carbon dioxide, and water to make glucose their food, chemical energy, and they release oxygen as a waste product. It basically powers almost all life on Earth.
Provides the energy and the oxygen.
Exactly. Respiration, which was mentioned too, is kind of the reverse, breaking down glucose to get energy out. Plants do both, by the way.
Okay. Vitamins next. Question 7 links vitamin A deficiency with night blindness. Why that specific connection?
Vitamin A is crucial for making a pigment in our eyes called rhodopsin. It's in the rod cells of the retina, the ones we use for vision in dim light.
Ah, so no vitamin A, no rhodopsin.
And you struggle to see when it's dark. Direct link between the nutrient and a specific function.
Makes sense. Then questions 20 and 207 talk about iron deficiency and anemia. What's iron's role?
Iron is central to hemoglobin. That's the protein in red blood cells that actually grabs onto oxygen and carries it around your body.
So less iron means less hemoglobin.
Means your blood can't carry enough oxygen. That leads to anemia, feeling tired, weak, because your tissues aren't getting enough OO.
And the question contrasted this with things like goiter.
Right, goiter is iodine deficiency affecting the thyroid. Scurvy is vitamin C. Beriberi is vitamin B1. Shows how different nutrients have very specific jobs.
Okay. Questions 32 and 47 mention tuberculosis as a bacterial disease and compare bacteria to viruses, fungi, parasites.
Good overview. It's important to know what kind of microbe is causing an illness. Bacteria like TB are living cells. Viruses, like for measles or flu, are different. They need our cells to reproduce. Fungi cause things like ringworm. And parasites, like for malaria, are often more complex organisms. They need different treatments.
Right. Let's look at the eye. Question 17 focuses on the iris, the colored part. What does it do?
The iris works like the aperture on a camera. It controls the size of the pupil, that black hole in the center.
Letting more or less light in.
Exactly. In bright light, it constricts the pupil to limit light entry. In dim light, it dilates it to let more light reach the retina at the back, where the actual light detection happens. The lens focuses it, the cornea protects and helps focus too.
Okay. Moving inside the body. Question 39. The functional unit of the kidney is the nephron. What are these?
Kidneys have millions of these tiny filtering units called nephrons. They're the real workhorses. They filter waste out of your blood, balance fluids and salts, and make urine. Incredibly efficient little structures.
Millions of them.
Yeah, amazing filtration system.
Question 43 says the liver is the largest gland. It seems to do a lot.
Oh, it's a powerhouse. Hundreds of functions. Makes bile for digestion, detoxifies blood, stores energy like glucose, makes vital proteins. It's involved in so much metabolism, way broader functions than, say, the pancreas or thyroid gland alone.
We mentioned iodine and goiter earlier. Question 45 nails that connection down again.
Yeah, iodine is essential for making thyroid hormones, which control your metabolism. Not enough iodine, the thyroid gland can swell up trying to compensate. That's a goiter. Classic deficiency sign.
Simple cause, visible effect. Question 88 talks about amoeba reproducing by binary fission.
Right, that's asexual reproduction. The single amoeba cell just splits into 2 identical copies. Very simple, very efficient for single-celled life. No partners needed.
Just divides.
Just divides. Multicellular organisms have other asexual methods too, like budding or fragmentation sometimes.
Question 92 gets fundamental. The unit of heredity is the gene.
Genes are segments of DNA. They hold the instructions, the code for building proteins. And proteins do almost everything in the body, determining our traits. Genes are strung together on chromosomes inside our cells.
The blueprint,
The
essentially.
blueprint, exactly.
Question 98 mentions rabies from an animal bite. A scary one.
Very serious viral disease affecting the brain and nervous system. Almost always fatal once symptoms show, which is why getting treatment immediately after a potential exposure is critical. And vaccinating pets helps prevent spread.
Definitely. Back to vitamins. Questions 85 and 235 link vitamin D deficiency with rickets, especially in kids.
Yeah, vitamin D is vital for absorbing calcium and phosphorus, the minerals needed for strong bones. Without enough D, especially during growth, bones can become soft and weak, leading to rickets and potential deformities.
Need D to use the calcium.
Pretty much, yeah.
Questions 148 and 257 cover vitamin C deficiency and scurvy, another classic.
Vitamin C, or ascorbic acid, is needed to make collagen. That's a protein that's like the glue holding tissues together, skin, blood vessels, bones. Without C, you get scurvy. Bleeding gums, poor healing, fatigue. Big problem for sailors historically.
Before they knew about citrus fruit.
Exactly.
Questions 135 and 267 talk about vitamin B1, thiamine, and beriberi, also pellagra and B3, the B vitamins theme complex.
They are a group, yeah. B1, thiamine, is key for energy metabolism and nerve function. Deficiency causes beriberi, affecting the heart and nerves. B3 niacin deficiency causes pellagra, with skin issues, digestion problems, even dementia. The 3Ds, different B vitamins, different jobs.
Question 61 gives the chemical name for vitamin C, ascorbic acid.
Good to know the chemical names, too. Ascorbic acid is C. Retinol is A, thiamine B1, calciferol is D. You see these on supplement labels.
Right. Questions 56 and 185 mention vitamin K's role in blood clotting.
Very important. Vitamin K is needed by the liver to make several proteins, clotting factors, that are essential for blood coagulation. Without enough K, you can have problems with bleeding.
Okay. Question 53. The basic structural and functional unit of life is the cell.
The absolute foundation of biology. The smallest thing that can carry out all life processes. Cells group together to form tissues. Tissues make organs. Organs work together in organ systems. Levels of organization.
From simple to complex. Question 257 briefly mentions vitamin E deficiency. What does E do mainly?
Vitamin E is primarily an antioxidant. It helps protect cell membranes from damage by unstable molecules called free radicals. Deficiency is rare, but can potentially lead to nerve and muscle issues over time.
Protection at the cellular level.
Yeah.
Question 258 talks about plant transport. Xylem for water and minerals. Phloem for sugars, like pipes.
Very much like a plumbing system. Xylem tubes pull water and dissolved minerals up from the roots. Phloem tubes transport the sugars made during photosynthesis down from the leaves to wherever the plant needs energy or storage.
Up and down transport. Got it. Question 198 links vitamin B12 deficiency to pernicious anemia. How's that different from iron deficiency anemia?
B12 is needed for making healthy red blood cells and for nerve function. Pernicious anemia is often caused by the body not being able to absorb B12 properly. It leads to fewer but abnormally large red blood cells and potential nerve damage. Iron deficiency just affects the hemoglobin within the cells. Different causes, similar outcome of anemia, but B12 has the nerve aspect too.
Okay, different root cause. Question 196. Insulin's role in regulating blood sugar ties into diabetes.
Absolutely critical. Insulin from the pancreas acts like a key, allowing glucose from your blood to enter your cells to be used for energy. Without enough insulin, or if cells don't respond to it, glucose builds up in the blood. That's diabetes.
Maintaining that balance.
Glucose homeostasis, yes.
Question 203 covers anaerobic respiration in yeast, making ethanol and CoO, different from what happens in our muscles.
Yeah, both happen without oxygen,
Yeah.
anaerobic. Yeast fermentation produces alcohol, ethanol, and carbon dioxide used in brewing and baking. Our muscles, during intense exercise when oxygen runs low, produce lactic acid instead. That contributes to muscle fatigue. Different end products.
Different ways to get energy without air.
Exactly.
Last one in biology. Questions 51 and 208 explain transpiration water loss from plants via stomata.
Stomata are tiny pores, mostly on leaves. Transpiration is water evaporating out of these pores. It sounds like a loss, but it's crucial. It creates the pull that draws water up the xylem from the roots, and it also helps cool the plant down.
So evaporation drives water uptake.
In large part, yes.
All right, fantastic. Let's pivot to chemistry and materials.
Yeah.
Question 3 starts us off simply. Chemical symbol for water, H0.
H0, 2 hydrogen atoms, 1 oxygen atom. Seems simple, but the way they bond gives water all its amazing properties, dissolving things, high heat capacity, essential for life as we know it.
Couldn't live without it. Question 5. Lightest metal is lithium. Why so light?
Lithium, light just has a very small, light atom, only 3 protons. Low atomic mass means low density, it floats on oil. That lightness is key for batteries in phones and laptops.
Right, lightweight power. Question 6. Carbon dioxide is the main greenhouse gas. How did that work? Again, briefly.
Greenhouse gases like heliuro trap heat in the atmosphere. Sunlight warms the Earth, Earth radiates heat back out, but coheura absorbs some of that outgoing heat, keeping the planet warm. More carryo, more heat trapped.
Like a blanket.
A thickening blanket, yes, due to human activities increasing TO's levels.
Question 13. Diamond is the hardest natural substance because of its structure.
Exactly. Every carbon atom in diamond is bonded super strongly to 4 others in a rigid 3D tetrahedral network. Makes it incredibly hard and resistant to scratching.
Okay. Question 16 and 234 give us NaCl, common salt.
Sodium chloride. An ionic compound, positive sodium ions, Na, and negative chloride ions, SiO, held together in a crystal structure. Essential nutrient and, of course, used for flavoring.
Question 21. Baking soda is NaToS. How's that different from washing soda?
Baking soda is sodium bicarbonate. Washing soda is sodium carbonate, NaTo. Similar names, but washing soda is a stronger base, more alkaline, used for cleaning, while baking soda is for baking or as an antacid.
Bicarbonate versus carbonate. Got it.
Yeah.
Question 23. Sublimation. Solid straight to gas.
Yep, skips the liquid phase entirely. Dry ice. Solid CORO is the classic example. It just vanishes into gas at room temperature. Mothballs do it too.
Question 24 identifies carbon as a non-metal. What's the main difference between metals and non-metals?
Generally, metals conduct heat and electricity well. They're shiny, malleable, ductile. Non-metals usually aren't good conductors. They can be gases or brittle solids, not shiny. Carbon's mostly like a non-metal, except graphite conducts electricity.
Right. It's a bit unusual. Questions 11 and 44. Biogas is mainly methane, CH. Where does that come from?
Biogas is made when organic stuff like farm waste or sewage breaks down without oxygen, anaerobic digestion. Microbes munch on the waste and produce methane, which you can burn for energy.
Turning waste into fuel.
Pretty much.
Question 12. pH of pure water is 7. What does that mean?
pH 7 is neutral. The scale goes from 0, very acidic, to 14, very basic alkaline. Neutral means it has equal amounts of acidic hydrogen ions and basic hydroxide ions. Perfectly balanced.
Okay. Question 38. Brass is an alloy of copper and zinc. Why mix metals together like this?
Alloys are mixtures made to get better properties. Pure copper is quite soft. Adding zinc makes brass, which is harder and resists corrosion better. Steel, iron plus carbon, is way stronger than iron. Bronze, copper plus tin, is durable. You tailor the properties by mixing.
Getting the best of both worlds.
We're creating entirely new properties, yeah.
Graphite shows up again in question 42 as a moderator in nuclear reactors. How does it moderate?
In a reactor, nuclear fission releases fast-moving neutrons. Graphite is good at slowing these neutrons down through collisions without absorbing too many. Slower neutrons are better at causing more fission, keeping the chain reaction going controllably.
Slowing down the reaction bullets.
That's a decent way to put it, yeah.
Question 52. Sulfuric acid. HERO0. A major industrial chemical.
Hugely important. Very strong acid used to make fertilizers, plastics, detergents, refined oil, processed metals. It's everywhere in industry. A real workhorse chemical.
Question 54. Mercury is the metal that's liquid at room temperature. Why just mercury?
It's down to its electron structure. Mercury's electrons are arranged in a way that leads to weaker bonds between its atoms compared to other metals, so it doesn't take much heat for the atoms to slide past each other, hence liquid.
Weak bonds make it runny.
Essentially, yes.
Question 27. Nitrous oxide, aneuro, is laughing gas, used in medicine.
Yeah, it has anesthetic and pain-relieving effects, used often in dentistry and minor procedures for sedation. The laughing gas name comes from the euphoria it can cause.
Questions 33 and 248. Glucose, CH0, a monosaccharide, the basic fuel.
The primary fuel for most life, yes. It's a simple sugar, a single unit. Carbohydrates we eat get broken down into glucose, which our cells burn for energy via respiration.
Question 84. Ammonia is NHOs, used for more than just cleaning supplies.
Oh, massively. Its biggest use is making nitrogen fertilizers absolutely vital for feeding the world's population, also used in plastics and explosives manufacturing.
Wow, okay. Question 97. Sodium hydroxide, NaOH, also called lye.
Right. Or caustic soda. It's a very strong base, very corrosive, used to make soap, paper, textiles, and it's in things like drain cleaner because it breaks down grease and hair.
Strong stuff.
Handle with care.
Questions 134 and 237. Acetic acid, chase OH, is in vinegar.
That's what gives vinegar its sour taste and smell. It's a weak organic acid, usually about 5% concentration in vinegar, made by fermenting ethanol.
Question 90 says burning wood is a chemical change, unlike melting ice. Physical change. What's the core difference?
Chemical change means new substances are formed. Burning wood reacts with oxygen to make ash, KORO, water vapor, completely new stuff. Physical change, like melting ice, just changes the state, solid to liquid, but it's still HRO. No new chemicals are made.
New stuff, chemical change. Got it. Question 94 identifies helium as a nodal gas. And question 191 says it's used in deep-sea diving mixtures. Why helium?
Noble gases have full outer electron shells, making them very unreactive or inert. Helium is also very light and doesn't dissolve well in blood under pressure. Divers breathing regular air deep down can get nitrogen narcosis, drunk feeling, and the bends when surfacing. Helium avoids these problems.
Safer for deep dives.
Much safer.
Question 147 gives sodium carbonate again, washing soda.
Right, the stronger cousin of baking soda. Used in detergents, making glass, softening water due to its alkalinity.
Question 184 covers carbonic acid, H-heroes, forms when KORO dissolves in water.
Yes. It's a weak acid, but important. It helps buffer our blood pH, keeping it stable. It also weathers rocks over long periods. Fizzy drinks have it too.
Question 194 identifies iron as a transition metal. What's special about transition metals?
They're that block in the middle of the periodic table. They often form colored compounds, can have multiple charges, oxidation states, and many are good catalysts, speeding up reactions. Iron, copper, gold, silver, all transition metals.
Okay. Question 197. Magnesium hydroxide, MgOH, milk of magnesia, used as an antacid.
Yes, it's a mild base. It neutralizes excess stomach acid, relieving heartburn. Also works as a laxative in higher doses.
Question 200 identifies sodium oxide, NaO, as a basic oxide, as opposed to acidic oxides.
Right. Oxides of metals, like sodium, tend to be basic. They react with acids. Oxides of nonmetals, like carbon dioxide or sulfur dioxide, tend to be acidic. They react with bases. Some are in between.
Metal oxides are basic. Non-metal oxides are acidic, generally.
That's the general trend, yeah.
Question 264 gives ethanol, CaDOH, the alcohol in drinks.
That's the one. Produced by yeast fermentation, as we discussed. Also used widely as a solvent, a fuel, like in E10 gasoline, and a disinfectant.
Question 210 says steel is a mixture, an alloy, not a pure substance like graphite.
Right. Steel is mostly iron mixed with carbon, and often other metals like chromium or nickel. Because the components aren't chemically bonded in a fixed ratio, it's a mixture, specifically an alloy. Graphite is just pure carbon atoms arranged one way. Diamond is pure carbon arranged another way. Those are pure substances, elements.
Mixture versus pure substance. Important distinction.
Very. Affects properties and how we classify materials.
Question 234 gives sodium chloride, NaCl again, just reinforcing its importance.
Can't escape salt.
Question 244 identifies aluminum oxide, LOERO, as amphoteric. What's that mean?
Amphoteric means it can act as either an acid or a base. Aluminum oxide will react with strong acids and it will also react with strong bases. It swings both ways, chemically speaking. Zinc oxide is another example.
Dual nature. Okay. Question 250 calls nitric oxide, NO, a neutral oxide.
Yeah, meaning it doesn't really react with acids or bases to form salts, doesn't show significant acidic or basic character. Carbon monoxide, CO, is another neutral oxide.
Question 254. Sucrose, table sugar, CaO, a disaccharide, meaning two sugars joined.
Exactly. Di means two. Sucrose is made of one glucose unit chemically bonded to one fructose unit. Glucose and fructose themselves are monosaccharides, so sucrose is a double sugar.
Simple sugar versus double sugar.
Right.
And finally, for chemistry, question 190 says burning fuel is exothermic, releases heat.
Yes. Exothermic reactions release energy, usually as heat, into the surroundings. Burning wood, gas, oil, they all get hot because the chemical reaction releases energy. Endothermic reactions, less common in daily life, absorb heat and feel cold.
Okay, that covers a lot of chemistry. Let's move to our fourth theme, physics and general science principles. Question 8. Speed of light is maximum in a vacuum. Why there?
In a vacuum, there's nothing for light to interact with, no atoms or molecules to bump into or get absorbed and re-emitted by, so it travels at its absolute top speed, c. In air, water, glass, it interacts with the material and slows down a bit.
Nothing to get in the way.
Pretty much.
Question 9. Power of a lens is measured in diopters, like on eyeglass prescriptions.
Exactly. The diopter measures how strongly a lens bends light. It's actually the reciprocal of the focal length in meters. A higher diopter number means a stronger lens, shorter focal length, bends light more sharply, used to correct focus onto the retina.
Question 10. Identify solar energy as renewable, unlike fossil fuels.
Key distinction. Renewable sources like solar, wind, hydro won't run out on human timescales. They're constantly replenished. Fossil fuels, coal, oil, gas were formed over millions of years, and we're using them up far, far faster than they're made. Finite resources.
Sustainable versus finite.
Exactly.
Question 15 says velocity is a vector quantity, unlike speed scalar. What makes it a vector?
Direction. A scalar just has magnitude, a size. Speed is just how fast, like 60 millibreller. A vector has magnitude and direction. Velocity is speed in a specific direction, like 60 millipart or north. That direction part is crucial in physics.
Speed versus velocity. Subtle but important.
Very.
Question 25. Work done has the unit joule, same as energy. Linked concepts.
Directly linked. Work is done when a force causes displacement. It's fundamentally a transfer of energy. When you lift a box, you do work on it, transferring energy to it, potential energy. So work and energy share the same unit, the joule.
Doing work, transferring energy.
That's the essence of it.
Questions 28 and 41 mention refraction light bending and link it to twinkling stars. How does bending light make stars twinkle?
Starlight travels a long way to reach us, and the last part is through Earth's atmosphere. The atmosphere isn't uniform. It has turbulent layers of air with slightly different temperatures and densities.
Right.
As starlight passes through these shifting layers, it gets bent or refracted randomly this way and that. To our eyes, this makes the star's apparent position and brightness fluctuate slightly. We see it as twinkling. Planets usually don't twinkle because they appear as tiny disks, not points of light, averaging out the effect.
Atmospheric wobbles.
Good way to think of it.
Question 34 covers conduction heat transfer through collisions, different from radiation and convection.
Yes, the three main ways heat moves. Conduction is heat transfer by direct contact, molecule-to-molecule bumping. Think of a metal spoon heating up in hot soup.
Okay.
Radiation is heat transfer by electromagnetic waves, like heat from the sun or a fire, travels even through vacuum. Convection is heat transfer by the movement of fluids, liquids or gases. Hot air rising is convection.
Touch, waves, or flow.
Nice summary.
Question 37. Gravity is strongest at the poles because the Earth isn't perfectly round.
That's the main reason, yes. Earth bulges slightly at the equator and is flattened at the poles due to its rotation. So the poles are slightly closer to the Earth's center than the equator is. Closer distance means slightly stronger gravity. Rotation also adds a small outward centrifugal effect, strongest at the equator, reducing apparent gravity there too.
Closer to the center, stronger pull.
Exactly.
Question 40 says the speed of sound is fastest in solids like steel. Why solids?
Sound travels as vibrations. In solids, the atoms or molecules are packed much closer together and linked by stronger bonds than in liquids or gases. This allows vibrations to pass from one atom to the next much more quickly. So, even though steel is rigid, sound zips through it faster than through air or water.
Tighter connections mean faster travel.
Precisely.
Graphite again in question 42 as a nuclear moderator. Slowing neutrons.
Yes. We covered that in chemistry, but it's a physics application too. Its structure allows it to slow down those fast fission neutrons efficiently so they can sustain the chain reaction.
Questions 55 and 149 cover pressure force per unit area. Unit is the Pascal.
Pressure is fundamental, especially with fluids. It's about how concentrated a force is. A sharp knife cuts well because the force is concentrated on a tiny area, creating high pressure. The Pascal, Newton per square meter, is the standard unit.
Force divided by area.
Yep.
Question 58 defines acceleration as the change in velocity per unit time.
Right. Acceleration isn't just speeding up. It's any change in velocity. So speeding up, slowing down, which is often called deceleration, or changing direction, or any combination. It's the rate of change of velocity.
Any change in speed or direction.
Correct.
Question 59 identifies silicon as a semiconductor, the heart of electronics.
Absolutely. Semiconductors like silicon aren't great conductors like copper, nor great insulators like glass. They're in between. But crucially, their conductivity can be precisely controlled, often by adding tiny impurities, doping, This control allows us to build transistors, the switches that are the basis of all modern electronics.
Controllable conductivity.
That's the key.
Question 62. Rectilinear propagation means light travels in straight lines.
In a uniform medium, yes. Light rays travel straight. This simple fact explains how shadows form, how pinhole cameras work, and is the basis for geometrical optics understanding lenses and mirrors.
Straight lines explain shadows. Makes sense. Question 89. Speed of electromagnetic waves in vacuum is the speed of light. Applies to radio waves, X-rays too.
All of them. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. They're all forms of electromagnetic radiation. They have different wavelengths and frequencies, but in a vacuum, they all travel at exactly the same speed, cm, a universal constant.
One speed fits all.
In vacuum, yes.
Question 193 explains the Doppler effect change in wave frequency due to motion, like an ambulance siren.
That's the classic example. The pitch sounds higher as the siren comes towards you, waves bunch up higher frequency, and lower as it moves away, waves stretch out lower frequency. It happens with light too. Light from galaxies moving away from us is shifted to lower frequencies, red-shifted, which is how we know the universe is expanding.
Sound and light both do it.
Any kind of waves, really.
Question 245 discusses total internal reflection, how fiber optics work.
Exactly. When light tries to go from a denser medium, like glass, to a less dense one, like air, at a shallow enough angle, greater than the critical angle, it can't get out. All of it reflects back inside. Fiber optic cables use this to trap light signals and guide them along the fiber with very little loss.
Light gets trapped inside the cable.
Bouncing along inside, yes.
Question 189 states the law of reflection. Angle of incidence equals angle of reflection. Always true.
For reflection, yes. Applies to mirrors, shiny surfaces, even rough surfaces if you look closely enough at how individual rays bounce. The angle the incoming ray makes with the perpendicular, normal, equals the angle the outgoing ray makes. Simple, fundamental law.
Incoming angle equals outgoing angle.
Measured from the normal, yes.
Question 143 links a star's color to its temperature. Hotter stars are bluer.
Yes. Hot objects glow, and the color of that glow depends on temperature. Really hot stars emit more blue and ultraviolet light, appearing blue-white. Cooler stars emit more red and infrared light, appearing red or orange. Our sun is yellowish-white, kind of in the middle. We can tell a star's surface temperature just from its color.
Color tells temperature. Amazing.
It's pretty neat, yeah. Black body radiation is the principle.
Question 95. Nuclear fusion happens in the sun. Hydrogen becoming helium.
That's the main process. Under the sun's intense core pressure and temperature, hydrogen nuclei fuse together to form helium nuclei, releasing enormous amounts of energy in the process. That energy is what makes the sun shine and ultimately powers life on Earth.
The sun's power source.
The ultimate power source for us.
Question 93 mentions dispersion and refraction in rainbow formation. How do they work together?
Sunlight entering a raindrop gets refracted, bent. But different colors bend by slightly different amounts. Blue light bends more than red light. That's dispersion, splitting the white light. Then the colors reflect off the back of the raindrop and refract again as they exit, separating the colors further into the arc we see.
Bending, splitting, reflecting.
That's the sequence.
Question 201 explains the Tyndall effect scattering of light by particles, like seeing sunbeams in dust.
Exactly. Tiny particles suspended in air, like dust or smoke, or liquid, like milk, are large enough to scatter light sideways. So if a beam of light passes through, you can see the beam's path because light is scattered towards your eyes. True solutions with dissolved molecules don't do this.
Particles make the beam visible.
Right.
And last in physics, questions 209, 259, 239 mention that the image from a convex lens depends on the object's position.
Yes, a convex lens, thicker in the middle, can form different kinds of images. If the object is far away, you get a small, inverted, real image, like in a camera. If it's very close, closer than the focal length, you get a magnified, upright, virtual image, like a magnifying glass. The image type changes depending on object distance relative to the focal length.
Where you put the object changes the image.
Completely. That's how lenses give us different functions.
Okay, final theme. Instruments and measurement. Questions 19 and 136 mention the barometer for atmospheric pressure.
Right. A barometer measures air pressure, the weight of the atmosphere pressing down, essential for weather forecasting, as changes in pressure often signal changing weather.
High pressure, usually good weather. Low pressure, maybe storms.
That's the general idea, yes.
Questions 29 and 255 cover the lactometer for milk density purity.
A lactometer is basically a hydrometer calibrated specifically for milk. It floats higher or lower depending on the milk's density, which can indicate how much water or fat is present, giving a rough idea of quality or adulteration.
Floating tells you density.
Exactly.
Question 86. The pyrometer measures high temperatures without contact.
Yes. Think measuring molten metal in a furnace or a kiln. You can't stick a regular thermometer in there. A pyrometer measures the infrared radiation emitted by the hot object to determine its temperature from a distance.
Measures the heat glow.
Essentially, yes, thermal radiation.
Question 136 brings up the hygrometer for relative humidity.
A hygrometer measures the amount of water vapor in the air, usually expressed as a percentage of the maximum amount the air could hold at that temperature. Important for comfort, weather, and many industrial processes.
How damp the air feels.
Right.
Question 186. The altimeter measures altitude, often linked to barometers.
Yes, many simple altimeters are essentially barometers. Air pressure decreases predictably with altitude, so by measuring the pressure, the altimeter can estimate the height above sea level. Pilots and hikers use them.
Pressure goes down as you go up.
Correct.
Question 265.
Yeah.
The sphygmomanometer measures blood pressure. That cuff thing?
That's the one. Usually with a cuff, a pump, a gauge, and used with a stethoscope. It measures the pressure in your arteries when the heart beats, systolic, and rests, diastolic. Vital health measurement.
Systolic over diastolic. Got it.
Mm-hmm.
Question 205. The venturimeter measures fluid flow rate. How's that work?
A venturimeter has a constricted section, a throat, in a pipe. As fluid speeds up through the narrow throat, its pressure drops. Bernoulli's principle. By measuring the pressure difference between the wide part and the throat, you can calculate the flow rate, used in industry to measure gas or liquid flow.
Narrower means faster flow, lower pressure.
That's the principle, yes.
And finally, question 215 mentions the hydrometer for measuring liquid density in general. Lactometer is one type.
Right. A hydrometer is the general instrument. It's a weighted float with a scale. You float it in a liquid, and the denser the liquid, the higher the hydrometer floats. You read the density off the scale. Used for battery acid, antifreeze, alcohol content, etc.
Simple float, lots of uses.
Very versatile.
Wow. Well, that brings us to the end of this particular deep dive. We've covered a huge amount of ground in general science, starting from those exam questions.
It really shows how interconnected everything is, doesn't it? Physics principles underlie chemical reactions, which drive biological processes. Units tie it all together.
Absolutely. And understanding these fundamentals, it's not just for exams, as you said. It gives you, the listener, a kind of framework for making sense of the world.
Yeah, you start seeing the science behind everyday things. Why the sky is blue, how your microwave works, why certain foods give you energy. It adds a layer of understanding.
So maybe a final thought for you to consider. As you go about your day, think about how these different threads, physics, chemistry, biology, measurement, weave together in the things you encounter.
Which area sparked your interest most? Was it the physics of light and energy, the chemistry of materials, the biology of life? Maybe think about what you'd want to explore just a little bit further.
This has been a really enjoyable exploration through these fundamentals. We hope it's given you some valuable insights and maybe whetted your appetite for more science.
Thanks for joining us on this deep dive. Until next time.